All right, let's try this exam style question on multi-step mechanisms and their rate laws. Okay, so we are given a net reaction, A plus B plus C goes to X, Y. Okay? And somebody has already gone into the lab and measured the experimental rate law and knows that the rate law is equal to some K value. Okay, so just whatever rate constant times A times B times C. Okay, so then we have four options, four different mechanisms, and we're asked to figure out which one is most likely the mechanism that explains this rate law. So we need to derive the rate law for each of these four mechanisms and then see which one matches up with that experimental rate law and makes the most sense. Okay, so let's begin with mechanism one. This is essentially, we're going to be doing a guess and check here. So we have two rules when we're writing rate laws for multi-step mechanisms. The first and the most important, I think, is to write the rate law from the slow step, okay, the rate determining step. So in this first case, I've got a slow step to start with and then a fast step. I don't care about that fast step because it's not going to determine my rate. The rate will be dictated by how long it takes for A plus B to become D. So the rate law here is just K times A times B. All right. And so this is our rate law. We're done here. It's very easy when your slow step is the first step. And that's not the observed rate law, right? It doesn't depend on C. So this can't be right. All right, let's consider this next one here. We've got A plus C is in equilibrium with D. That's a fast step. And then once D is created, then D reacts with B to make X and Y, and that's a slow step. So again, we're going to go here. We're going to say, write the rate law from the slow step. Okay, so we say rate equals K times P times D. And then we see, oh, wait, we've defined our rate law in terms of an intermediate. Notice that D doesn't show up in our net reaction. It is made in the first step and consumed in the second step. And generally, it's not good kinetics or like good chemistry to define a rate law using an intermediate. We want to use the reactants, the actual things that we added. So I need to rewrite D, and I'm going to use the equilibrium method for that. All right, so this is fast. These double arrows here mean that we've come to an equilibrium and we have a constant concentration of D that is determined by our concentration of A and C. So I'm going to write out my equilibrium method. Okay, so that K1, okay, so the forward rate constant times A times C equals, I'm going to call this K minus 1, so the reverse, how fast the rate constant for the reverse, times D. I would like to define D. Okay, so I'm going to solve out for D just by dividing both sides by K minus 1. So I'm going to get the concentration of D is equal to K1 over K minus 1 A times C. And now I can take this and plug it in here, okay? So I now have the rate equals some K value, and we could define that specifically now. If I had called this K2, we would have K2, K1 divided by K minus 1, and it would depend on the concentrations of A, B, and C. And that is, notice that yes, we do have this like big thing, but I could just call that K observed. But this is the rate law that was experimentally observed. Okay, so 2 is in contention here. Like it does make sense. That would be consistent with the experimental rate law. I'm going to check the last 2 just to make sure that something funky is not happening. But so far, 2 is a viable option. All right, so let's look at 3 here. And 3 has one step, and it's importantly, you will notice it is termolecular. Okay, so I'm expecting 3 things to come together in space with the right orientation and enough energy to clear some barrier. Termolecular steps are really unlikely, so this is probably very slow. Like so slow that's not feasible. But I could write a rate here and it would be rate equals K, A, B, C. And that is also consistent with what we observed. But it is not feasible. It's unlikely. Here it says most likely. I would not consider this a most likely mechanism because it's depends upon a termolecular step. And that just doesn't happen very regularly, if at all. Okay, so you've got one more here. This is a three-step mechanism. We, again, per our most important rule, write the rate law from the slow step, find the slow step, and then we work backwards. Anything after the slow step, like this, we have another fast step afterwards, we don't care about it in terms of writing. Of course, we care about it, it's not necessary to consider when we write the rate law. So you find the slow step and then you work backwards. So here I'm going to have the rate equals K2 B times D. And that gives me a rate law. But again, I've noticed that I've defined it by D, which is not a reactant. It's an intermediate. I don't want an intermediate. So I'm going to go back and define it using the equilibrium method, just like we did in step 2, or for mechanism 2. But now I'm going to have K1 times A equals K minus 1 times D. It just depends on A here, converting to D. And so I could get a D equal to K1 over K minus 1 times A. This is what would get plugged in here. And so we would have a rate law of rate equals, and this will be K2, K1 minus K minus 1. Again, we can just shorthand that as K obs, just some K constant, some number is there, times A times B. And we don't have the dependence on C like we do in the experimental rate law that was observed per the introduction of this question. And so that's also not correct. Notice it actually has the same rate law as 1, but it would have a different K value, but that's not right either. So I'm looking for mechanism 2 here as our correct answer.